So this exercise we will do in several parts. Could have done it as different exercise, doesn't matter. So V is a non-linear space and W contained in V is a subspace. And I am going to define W perpendicular as set of all F in V star. So it's a subspace of V star such that FW is 0 for all W in W. Then W perp is a closed subspace. So this is almost immediate. So subspace, okay, by linearity. So if F and G, then all are in W perp. Alpha F plus beta G acting on W will also be 0, and therefore it is a subspace. And what about closure? Suppose Fn goes to F in V star, Fn in W perp. Then for every W in W, you have Fnw equal to 0, implies F of W is 0, implies F belongs to W perp. So W perp is closed. So this is a closed subspace. Okay. Next part of this exercise is very interesting. Show that, so F in V star, show that the distance of F from W perp is nothing but the norm of F restricted to W in W star. So what is the distance of F from W perp? This is nothing but the infimum over all G in W perp, norm of F minus G, and that norm is of course in V star. So let us take W in W, then F of W can be written as F of W minus G of W for all G in W perp, because if G is in W perp, this is always equal to 0. Therefore, mod FW is less than or equal to norm of F minus G V star norm W, and therefore you have norm of F in W is in W star is less than or equal to norm F minus G for all G, and therefore less than or equal to inf G norm of F minus G, G in W perp, and that is equal to D of FW. So we have one inequality. Conversely, let H belong to V star be a Hahn-Banach extension, that is such that H restricted to W equals F restricted to W, and norm of H V star is norm of F restricted to W in W star. This is just Hahn-Banach applied to F restricted to W. Then F minus H, both of them are agreeing on W, so this belongs to W perp, and you have D of FW perp is therefore less than or equal to norm of F minus H, which is equal to norm H, and that's equal to norm of F restricted to W in W star. So you have the reverse inequality. So on one hand you have this one, On the other hand, you have this, and that proves the result here. Okay. So let F belong to W star, and then let F tilde be a Hahn-Banach extension. What is that? F tilde is in V star, F tilde restricted to W equals F, and norm of F tilde equals norm F. This in V star and this in W star. So define sigma from W star to V star by W perp. W perp is a closed subspace, so this quotient is well defined, and this is nothing but sigma of F equals F tilde plus W perp. Show that sigma is well defined and an isometry onto V star by W. So what does this theorem say? So W star to V star by W perp is an isometric isomorphism because it becomes now onto, it's an isometry, so it's 1 to 1, onto it's isometry, so it's bicontinuous. Consequently, the dual of the space can be thought of as V star by W perp. So we have identified, we have computed the dual. So in last set of exercises, given V and W, we computed the dual of the product V cross W. The dual was V star cross W star, and we saw what is the norm we should put there. Now we are taking a subspace and we are identifying the dual. The dual is nothing but V star quotiented out by W perp. So that is an isometric isomorphism, and we have computed the dual. Okay. So you take, proof. So Hahn-Banach extension is not unique. So if you have F1 tilde, F2 tilde, two Hahn-Banach extensions, that means they agree on W. So F1 tilde minus F2 tilde belongs to W perp. So this implies that F1 tilde plus W perp equals F2 tilde plus W, and therefore sigma is well defined. The coset which we get does not depend on the Hahn-Banach extension, and therefore it is well defined. Okay. Now what is norm sigma F? This is norm of F tilde plus W perp, and we saw this is nothing but d distance of F tilde from W perp, and this is equal to norm of F W star. This is exercise B. Therefore sigma is an isometry. Finally, we have to check that it is surjective. Okay. So let F tilde plus W perp belong to V by V star by W perp. So let G be a Hahn-Banach extension of F tilde restricted to W. So, G also agrees with F tilde on W, and therefore G minus F tilde belongs to W perp, and therefore G plus W perp equals F tilde plus W perp. But then what is sigma of F tilde restricted to W? That is nothing but you take the Hahn-Banach extension, which is G plus W perp by definition, and that is nothing but F tilde plus W perp. And therefore, every element in this space, in this quotient space, is sigma of something, therefore sigma is onto. And that proves the theorem completely. So, we have identified the dual of a product, we have identified the dual of subspace. Now we want to identify the dual of a quotient space. Okay, so that is the next item on the agenda. So that is the part D of this. So W contained in V closed. Only for closed subspace we can define the quotient. So we define pi from V to the quotient space. This is the usual projection. So pi of x is x plus W. So F belongs to V by W star. Let F belong to the quotient space. Define tau of F equals F composed with pi. So pi will take you, so this is from this goes from V to the quotient space to R. So this is in fact in V star. Show that range of tau is in fact W perp, and that tau from V by W star to W perp is an isometric isomorphism. So it is onto and an isometry, and therefore we have now the quotient space. The dual of the quotient space is very simple. It is nothing but the perpendicular of W. So that is a very beautiful characterization. So solution or proof. So you take W in W, and let us take tau F acting on W. This is F of pi W, but pi W is nothing but the zero element. Pi W, W is in W, so pi W is zero element, and therefore this is F of 0 is equal to 0. Therefore tau F belongs to W perp. Okay, so range of tau is contained in W perp. Now let F belong to W perp. We want to show that it is tau of something. So you define capital F from V by W to R, namely F of x plus W equals F of x. So now again we have to check it's well defined, because when we take x plus W equals F of x, we are depending on the representative from the coset which we are taking, and we have to show that it is the same. So if x1 plus W equals x2 plus W, This means that x1 minus x2 belongs to W. So f of x1 equals f of x2. So capital F of x1 plus W equals f of x1 equals f of x2 equals capital F of x2 plus W. So if you have two cosets equal given by different representatives, it does not matter, the answer is finally the same. So this is well defined. And also, what is mod f of x plus W? Equals mod fx, which is mod of f of x plus W for all W in W, because f belongs to, since f belongs to W perp. And therefore, this is less than or equal to norm f times norm of x plus W. This is true for all, so I can put inf norm of x plus W, W in W, and that is equal to norm f times norm of x plus W. Therefore, capital F so this shows that f belongs to V by W star. And what is tau f at x? This is nothing but f of pi of x, that is equal to f of x plus W, and that is equal to f of x, and therefore tau f equals f. So this implies that tau is on 2s. And you also have that norm tau of f is less than or equal to norm f. Because tau of x is f of x, okay. Finally, we have mod f of x plus W equals mod tau f of x equals tau f of x plus W small w for all W in W, and that is equal to, less than or equal to, norm tau f times norm of x plus W, and this is true for all W, and therefore mod f of x plus W is less than or equal to norm tau f times norm of x plus capital W, and this implies that norm f is less than or equal to norm of tau f, and we had the other inequality before, and therefore we have norm of f equals norm of tau f. Therefore, the dual of the space is always the nothing but the orthogonal of W. Okay, so that is dual of the quotient space. So next exercise A. This is a remark I should have already made, but anyway we will do it as an exercise. So V non-linear space, and you have or let us take Banach, because we know in that case it is definitely exists, and phi from 0 1 to V continuous. Then we know that the integral exists. So, then integral 0 to 1 phi t dt is uniquely defined. So, what is the definition of the integral? It is if y equals integral 0 to 1 phi t dt means what? F of y should be equal to integral 0 to 1 f of phi of t dt for every f in V star. So, if you had two vectors I equals 1 2, then fyi, so this implies that fyi y1 equals fy2 for all f in V star, but we know that V star separates points. So, therefore, this implies y1 equal to y2 since V star separates points. So, we can always talk of the integral. That is what I have been doing, and I should have mentioned this earlier, but anyway it is good to do it as an exercise. Okay. So, B. So, what did we see? How was the integral defined? Namely, every continuous linear functional should go through the integral. So, that is what we saw. And now we will show that in fact every continuous linear operator also goes through the integral. So, VW norm Banach spaces and phi 0 1 to V continuous, then A belongs to LVW, it is a bounded linear operator from V to W. Then A of integral 0 to 1 phi t dt is equal to integral 0 to 1 A of phi t dt. So, A composed with phi is now mapping from 0 1 into W. So, A composed with phi maps 0 1 to W and is continuous. So, the left hand side makes sense, the right hand side also makes sense, this is a vector. So, I can apply A, and so we see that A has to go through the thing. Okay, so now let us take any f in W star. Then f composed with A belongs to V star. So, f composed with A of integral 0 to 1 phi t dt, by definition this should be equal to integral 0 to 1 f composed with A phi t dt. Now, f is any element and A composed with phi is a continuous function. So, by definition of the integral again, this is integral f times integral 0 to 1 A of phi t dt. And this is true for all f. So, f separates points. This implies A of integral 0 to 1 phi t dt equals integral 0 to 1 A of phi t. Okay. So, we will now do one last exercise 10. It is a very nice exercise which has lot of applications. So, V is a vector space, F0, F1, Fn linear functionals. There is no question of continuity now because we are only having a vector space such that intersection I equals 1 to n kernel of Fi is contained in kernel of F0. then there exists alpha 1 to alpha n in R such that f naught is equal to sigma I equals 1 to n alpha I fi. So f naught, this condition just implies that f naught has to be a linear combination of the fi's. So solution, so you define T from V to Rn plus 1. So T of x is f naught x, f1 x, fn x. So T is linear. So T of V is a subspace of Rn plus 1 and everything is finite dimensional, therefore closed. Okay. Now hypothesis implies 1 0 0 is not in the range of T. What happens if 1 0 0 is in the range of T? That means f1x, f2x, fnx are all 0. That means x belongs to the intersection of the kernel. Therefore, it should belong to the kernel of f naught, and therefore f naught x must be 0, but f naught x is equal to 1. So that is not possible. So this is not in the range. So by Han-Banach, there exists a continuous linear functional phi, continuous linear functional on Rn plus 1 such that phi restricted to Tv is identically 0 and phi on 1 0 0 0 is not 0. But what is a continuous linear function? There is nothing but Rn plus 1 dual is itself. So continuous linear functions again n plus 1 scalar, that is there exists beta naught beta 1 beta n in R such that sigma beta I equals 0 to n beta I, any element of Tv is fi of x is 0 for all x in V, but this beta should not vanish on 1 0 0 0, that means beta naught is not 0. So now it is immediate, you have that f naught of x is therefore equal to minus sigma I equals 1 to n beta I by beta naught times fi of x. So you just have to take alpha I equals minus beta I by beta naught and you are through. So these are some of the exercises. There are many more exercises in the book which I mentioned to you, functional analysis in the TRIM series. So and in many other books too. So it is good for you to try some of them. Thank you.